So welcome all. This is week 8 tutorial for the course Basic Linear Algebra. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. So this week I don't have anything new to cover, but I'll try to revise through everything that we have done throughout the course. I'll try to briefly go through each and every topic which I feel is important, not only from a perspective of this course, but if you are using linear algebra later on in somewhere in your life. Okay. Monitoring the chat box, so you can ask anytime. Okay. So let's begin. So when you started with this course of linear algebra, the first thing that you might have came across was system of linear equations. Okay. So in my opinion, linear algebra is nothing but a study of system of linear equations, and let's focus some time on how do we infer whether a system of linear equation has a solution or not, and those kind of things. Okay, let's say we have some sample system of linear equation. Let's say, so why is it called linear? Because the variable that is appearing has power 1 in it, right? So that's why this kind of system, these kind of equations are called linear. And when we have more than one such equations, we call it as a system of linear equations. Okay. So the first question that revolves around a system of linear equation is whether that system is consistent or inconsistent. Okay. So what do we mean by a consistent system of linear equation? So if solution exists, so if you are given with a system of linear equation and you are able to find x1, x2, x3 in this case, or let's say x1, x2, xn in generalized case, if you are able to find any solution satisfying the system of equation, then that system of equation is called consistent. Okay. And if you are not able to find solution, then that system is called inconsistent system of equation. Okay. So this is just a basic thing, but whenever a question get asked in the exam, they will mention consistent and inconsistent rather than if a solution exists or not. Okay. So let's say you have some equation in two variable, let's say, and then it is very easy for you to check whether a equation would exist or not. You can take one variable on the one side and then put it in the other. But let's say you have many variables and many equation, then it sort of becomes slightly more calculation heavy when you want to check whether a system is consistent or inconsistent. Then in those kind of case, you look towards matrices. So if you represent a system of equation in matrix, then you can use all the theory related to matrix algebra, and you can use them to infer whether your system is inconsistent or not. Okay, or whether it's consistent or not. So how do we convert a system of equation into matrix? Let's first let's look at it. How do we convert? So let's say you have an equation like this. What you do is you write the coefficients of all the variables appearing in the first equation as your first row, right? So you can write 1, minus 2, and 1. Here you can write 0, 2, minus 8, minus 4, 5, 9, multiplied by x1 into x2, x3. This is equal to 0, 8, minus 9. Okay. So now we have written it in form of ax is equal to b, right? So if you want to, let's say you pre-multiply both the side by A inverse, what you obtain is, this is A inverse into A inverse B. Okay. So this means that your x is nothing but A inverse of B. So if you want to check whether a like system is consistent or not, that you can do by just checking if this matrix A that you have constructed is invertible or not. Okay. So if inverse exists, then your system becomes consistent. If inverse doesn't exist, then your system becomes inconsistent. I won't say that. So there can be cases where you have infinitely many solutions. In those cases also, your system of equation, this A need not be invertible. I'll get into detail of it. Need not be invertible. Okay. So once you have a written matrix representation of your matrix, you can form a matrix called augmented matrix. Okay. I am just trying to throw terms so that it kinds of get revised for you, and you recall the concepts that you have done throughout the course. Okay. So what we do in augmented matrix is we write A augmented with B. So for example, in this case, you will write augmented matrix like 1 minus 2 1 0 2 minus 8 minus 4 5 9 augmented with B, that is 0 8 minus 9. Okay. So what we actually do with these kind of matrices, we do some row operation on them to reduce them to row echelon form or row reduced echelon form. Okay. So yeah, so first of all, let's see how does a row echelon form matrix look like. So first I'll go through row echelon form. So if you have a matrix in row echelon form, first thing is, so let's say you have a matrix, right? So the leading non-zero entry in any row is called as the pivot element of that row. Okay. So for example, in this matrix, these, this, and this would be your pivot elements for this particular matrix, right? So what does row echelon form says? That every entry below a pivot element must be 0. Okay, this is the first rule. So if you look at this particular matrix, if this is my pivot entry, then everything below this should be 0. So we need to make this 4 as 0. Okay. Second rule is that, let's say, second rule says, let's say you have a matrix, right? And you have some rows. Let's say this particular row, so ith row,
every element below the pivot is 0, right?
this is the first rule. And the second rule is that if you have, let's say, for ith row, you have pivot at, I would say, in
Only
jth,
on the right side of pivot, first pivot.
in jth column, yes. Then for rows I plus 1, I plus 2, and so on, pivot must be on right of j. Okay. So these are two simple rules for your row echelon form, and by now you must be aware like how to convert a matrix to row echelon form. That can be done via elementary row operation. Okay, so what are your elementary row operations? So elementary row operations include that you can multiply any row by some non-zero element, right? You can't multiply it by 0, then everything would become 0. That would make no sense. So you can multiply it by any non-zero element. Okay. You can add any two rows. So you can add any row to any other row, right? And the third rule is that you can swap any two rows. Okay. So then nothing changes, right? So let's take a very simple rudimentary example of 2 cross 2 matrix. Yeah. So if you see, for the first row, this is a pivot element. So I want everything below that to be 0. So I want to make this as 0. So what I can do is that R2 becomes, I'm subtracting 2 times of R1. Okay. I said we can add, but I also said we can multiply any row by any non-zero number. So that would lead to saying that we can subtract any multiple also. So if we do this, we obtain something like 1, 0, 2, minus 3. Okay. Now we have this pivot element. Oh, sorry, this is not a pivot element. Yeah. So for the second row, we have this pivot element. You can see that this pivot element is towards the right of the first pivot element. Okay. So both the properties of row echelon form are satisfied. So this matrix is in row echelon form. Okay. Okay, so now before moving to row reduced echelon form, let's recall some more things. Next thing is that how do we call a system consistent or inconsistent based on a matrix representation? Okay, so first of all, let's define what is rank of a matrix. There are many like equivalent definition, but the definition that I want to quote over here is, so let's say we have a matrix A, then rank of A is number of pivot element in row echelon form of A. So if you calculate the row echelon form of A, then the number of pivot elements that you have is your rank of that particular matrix. Okay. Now, coming back to our system of equation, let's say you have system of equation and you have converted it to matrix form, Ax is equal to B, then the system is consistent, okay, in two cases. So if it is consistent, it can have either unique solution or it can have infinitely many solutions. Okay. Also, the second case is that the system is inconsistent. Okay. Now, also, let's say you have n variables. You know that the number of variables is n. Okay. Now, you will have unique solution only in the case when rank of your matrix A is equal to n. Okay. So what you will do is you will form an augmented matrix out of it and you will try to convert it to echelon form. And you will observe whatever matrix that you have obtained, and using that you will check whether it's rank n or not. If it is rank n, then you have unique solution. Okay. If the rank is less than n and rank of A is equal to rank of A augmented B, okay, then in that case you have infinitely many solutions. Okay, what happened is that the rank of A came out to be less than n, but that was equal to your rank of A augmented with B. Okay, and inconsistent is the case when your rank of A is strictly less than n and rank of A is not equal to rank of A augmented B. Okay. I'll not take particular examples for every case, but what I'll do is that I'll take 1 2 cross 2 example just in case you are still not familiar with the process. Okay. So let's say we'll take a very simple example. Okay. Let's say x plus y is equal to 1 and x minus y is again equal to -1. Okay. This is a very fairly simple matrix. So if we want to represent it in form Ax is equal to b, then our matrix A is 1 1 1 minus 1, x is xy, and this is equal to 1 minus 1. Okay. And if you form augmented matrix out of it, what we obtain is, okay. Now we have this as a pivot element. We want to make this particular entry as 0. So what we will do is we'll do R2 goes to R2 minus R1. Okay. So yeah, so this entry becomes 1 and this entry becomes 0. Okay. Then this entry becomes 1, this entry becomes -2. Okay. And the same thing we'll do over here also. And this entry becomes 1, this entry becomes -2. Okay.
You're not audible. No.
Am I audible now?
Yeah. No.
Yeah, thank you for letting me know. Okay, what I was saying is like if I had -2 over here, in that case we came to inference that we have unique solution, right? Let's say for some example, we came up with a matrix so that we had 0 over here. Okay, now if you look at the part where we have a matrix, then we have only one pivot element over here, right? That is this one. So what would have been the rank of A? The rank of A would have been 1, right? But when we consider the augmented matrix AB, then we have two pivot elements. One is 1 and another one is -2. So then the rank of A augmented B is 2. Okay. So now because your rank of A is not equal to rank of A augmented with B, that's why this particular system is inconsistent. Okay. Also, let's say for some example, both these entries came out to be 0. Okay. Then rank of A is same as rank of A augmented with B, which is 1. In that case, your system is consistent and has infinitely many solutions. Okay. So if you have, let's say, a 3 cross 3 example, then also this is the way how you should approach it. Okay. 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 Now, I don't think there would be a straightforward question based on what is a vector space, but it is like useful, I would say, necessary to understand what a vector space is. So The second, probably the most important thing after the system of equations that you learned in this course was something called as vector space. Okay. So first thing is that a vector space is always defined over a field. Okay. What is a field? Field is a mathematical quantity satisfying some property. If you will go through some course on abstract algebra, then probably you will learn what a field is. Okay. But for now, what you can assume is that a field is something that looks like a real number, or let's say R2 or Rn, or complex numbers or complex to the power n. Also, your rational number, set of rational number is a field. You in linear algebra, you will encounter only these three fields, which are your rationals, real number, and complex number. Okay. Anything smaller than your rationals is not a field. Okay. So first of all, for a vector space, you need two things. Okay. You need a set of vectors and you need a set of scalars. This set of scalars is something that is called as your field. Okay. Now, here are some properties that these vectors need to satisfy. Okay.
Which is close under addition and scalar multiplication.
Yes. Though, so yes, you're true. Apart from these two things, you need two more things. That is your notion of addition and
And
scalar multiplication.
zero should be a part of it.
Yeah.
Zero vector.
Yes. So I think what you're saying is related to subspace. Let's say you are talking about some subspace of a space, then you need to check only these two things, that it is closed under scalar multiplication and addition, and it is and the zero vector is part of that space. But if you,
Actually,
yeah,
I studied this concept from some other source.
mm-hmm,
I mean, so there was a lecture from University of Colorado.
mm-hmm,
There is saying that a vector space is a subset S of Rn with the
mm-hmm,
following property, where zero is a subset of S and a zero vector of size n is in the set S, and
mm-hmm.
VW, which is the subset of S, then V plus W is a subset of S, and if alpha is an element of R, then V is a subset of, then alpha V is a subset of S. That is, S is closed under addition and scalar multiplication.
Understood your point. See,
So
what that, yeah,
these are the properties they explain to understand that what vector space really
I'll
is.
tell you what was happening there. So what they were trying to say is, so first of all, what you assumed is S is a subset of Rn, right? Now, one thing I can say is this Rn is already a vector space. Okay. So if you have some subset of a vector space, okay, then you need to check only those properties that you mentioned, that your alpha, let's say x plus beta y belongs to S if your alpha and beta belongs to your scalars. In this case, you can take real numbers, and x and y belongs to S. Then if this particular thing belongs to S, then your S will become vector space. What I am trying to say, this was covered in the last week, I think, of the lecture in this course. If you don't know anything about S, that it is subset of some other vector space or not, then how do you view that set? Okay.
Okay, got it.
Okay. Yeah. So
Thank you.
this is any arbitrary set V uh, with some scalar set S. I'll try to be more clear. Yeah. So let's say you have any arbitrary set V and you have a set of scalar called F. Okay. And these two things are necessary, that if you have, let's say, x comma y from a set V, then x plus y must belong to that set. That is, it is closed under addition, right? And also Cx belong to V, where C belongs to F and your x belongs to V, that it is closed under scalar multiplication. These two things are very necessary, right? But apart from these two things, it must satisfy these properties, that it must be commutative. This is the first property that you mentioned, and I also mentioned. The second property is that it should be commutative, okay, associative, existence of 0 and existence of identity. If you would have done any abstract algebra course, then you can say that this V is a group under addition. You can see all these properties are of a group, right? And the sixth property is that it should be closed under scalar multiplication that you again mentioned, right? And the last few points are just distributive properties, okay? And the last point is that it is associative under scalar multiplication and existence of scalar identity, okay? Sorry, multiplicative identity. Now I'll come to what you said, that some people introduce this vector space just by that particular definition, that 0 must belong to that particular set S. And if your x and y are belonging to the set S, then x plus y must belong to that set, and Cx must belong to that set. Some people also combine these two properties just to write Cx plus y belong to that particular set. Okay. So what I would suggest is we can just simply write one single statement that if W is a subset of some vector space V, we already know that this is a vector space. Then if W satisfies only this thing, that Cx plus By, where your C and B belongs to some scalars, this should belong to W. So you can take C is equal to B is equal to 0, then this would already like implicitly infer that 0 also belongs to your set C, right? So like if an exam it is to be asked anything related to vector space, then it should be something related to proving a particular set as a subset, or you might be given some properties and then you need to check whether a set satisfying these properties is a subset or not. Then you just need to check this thing, okay, that Cx plus By is a subset of that set for all C comma B in scalar set. This can be F if we generalize this, and then X comma Y belonging to W. Okay. One slight comment is that you can easily see why we just want to check that Cx plus By belongs to W. Okay. Why do we say this? I'll just highlight some of the points. Okay. Mhm. Huh. I'll hi why do we need only to check this particular property is, let's say your U and V are element of W. Okay. Now, because your W is a subset of V, then U and V are also element of bigger set V. So if all the elements of bigger set V is satisfying this particular property, because your V is already a vector space, then U and V also must satisfy this particular property, right? That's why if that's why your U plus V is always equal to V plus U. And the same thing holds for all these properties that I have highlighted, that this commutativity, associativity kind of hierarchically follow to the subsets. Okay. So that's why if you want to check only a subset, then you just need to check this particular property. Okay. So one of the intrinsic property of a vector space is its dimension. Okay. And for that we need to learn what a basis is, and to understand basis let's look at what do we mean by linear dependence and independence. Okay, I'll talk about linear dependence. Okay, so we talk about linear dependence of some vectors, so we call v1 v2 vn, let's say these are my vectors, we call them, so these are linearly dependent if there exists some scalars which are your alpha 1, alpha 2, alpha n, not all 0. By not all 0, I mean that at least one of these alpha i's must be non-zero. Okay, not all 0. such that alpha 1 into V1 plus alpha 2 into V2 plus alpha n into Vn is 0. So if you look at this kind of combination where you multiply a vector by some scalar and then you add, so you multiply vectors by scalar and you sum them together, this kind of combination is called as linear combination. Okay. So what I'm trying to say is, so if you have a linear combination of these vectors v1, v2, vn, which is summing up to 0, and whatever alpha is that you have obtained, not all of them are zeros, then you can say that this v1, v2, vn are linearly dependent. Okay, for example, if you look at vector 1, 1 and vector 2, 2, so let's call it v1, let's call it v2. So you know that minus 2 times v1 plus v2 would be 0. So these vectors v1 and v2 are linearly dependent. Okay. So now what is linear independence? So linear independence is just the opposite of dependence, that vectors which are not linearly dependent are linearly independent. Just to formally define, so v1, v2, vn are linearly independent if there exists no alpha 1, alpha 2, or I would quote it other way. So they are called linearly independent if alpha 1 v1 plus alpha 2 v2, if this particular combination is 0, then alpha 1 is equal to alpha 2 is equal to 0. So your all the alpha i's must be 0 for this particular thing to be 0. Then only you can say that your set v1, v2, vn are linearly independent. Okay. So there can be cases where you can be asked, I'm not sure whether this is a subjective exam or objective exam that you have to appear, but so if you are asked anywhere,
It would be
it would be
objective.
objective. Okay. So then this might not be useful, but yeah, it can be useful at many places. Like if you are asked to prove anything to be linearly independent, then the first step that you do is, so you let's say you have been asked to prove v1, v2, vn to be linearly independent and they satisfy particular properties, then you let alpha 1 v1 plus alpha 2 v2 plus alpha n vn to be 0, and then you prove that all your alpha is equal to 0. Okay. So this is what we mean by linear dependence and linear independence. Okay. Okay. Let's go to something called span of some set. Okay. So span is defined for some set S. Okay. Let's say you have set S having elements v1, v2, vn. Then span of S is defined as a1 v1 plus a2 v2 plus an vn, such that your a1, so all your ai's belong to your scalars. Okay. So what I mean is, so if you have some set of vectors v1, v2, vn, then you take linear combination of these vectors, all the linear combination possible, and you put it in a set. That particular set would be called as span of S. Okay. So for example, let's say you have you are talking about R2 and you have S as a single element set, that is your 1, 1. Okay. So
can we call it like a linear combination is like I mean range of that linear combination?
you can call it, like if you are looking at this linear combination as a function or operator, which which it is actually not, because when you talk about function, so for a unique input, you have a unique output, right? Which is not the case over here. But if you view it that way, then you can say it is range of that thing. So this won't be
Okay.
very technically correct, but what you are thinking is absolutely correct. Yeah. So if we have some set, let's say 1 comma 1, and so let's say uh, this is my this is my point 1 comma 1, then I take all the linear combinations. So if I multiply it by 0, then I get 0. I multiplied it by 1, I got 1. If I multiply it by half, I get half comma half, and so on if I multiply it by 2. So if you trace this thing, you will get a straight line. Like if you take the combination of all these lines, so the span of this set is this straight line, that is x is equal to y. Okay. So this is how this thing look like. If you had two linearly independent vectors over here, then the span would have been the complete of R2. Okay. Okay. So now what is a basis? We'll go to something called basis. Okay. Now basis is defined for a vector space. First thing. Okay. So let's say we have a vector space V. Okay. Then okay. So now the basis should satisfy two property. Okay. First of all, let's call the basis as beta. Beta is my notion that I'm using for basis. So the span of this basis set that I'm talking about beta, so this is a set, basis is a set that we would get, is your complete of V. Okay. And the second property is that if alpha is a proper subset, so this is not equal to. So if alpha is a proper subset of V, then span of alpha is not equal to V. So what it means is that your beta should span the complete vector space V, and if you even remove one element out of it, then it won't be able to span your complete vector space. So in some sense, it is the minimal set that is spanning your complete vector space V. That is called basis of your set. Okay. And something that comes with it is dimension of a vector space. So it is nothing but equal to the number of element in a basis. Basis set. So if you have a vector space, it is not necessary that you will have a unique basis. Okay. You can have more than one basis. This is very much possible. But one thing that would be unique is number of element in that basis. Okay. So if you have a, let's say two bases, beta 1 and beta 2, then for the same vector space V, then the cardinality of beta 1 must be equal to beta 2, that they must have same number of elements. Okay. So a particular vector space has unique dimension. Okay. So now, yeah, I want to mention some easy dimension for common vector spaces that you can use if questions are asked related to this. Okay. So first of all, for Rn, so I'm calling it easy dimension, but these are called standard basis. Okay. Okay. So for Rn, one of the standard basis is that you take 1 at the first element and then you take 0 everywhere else. For the second vector, you take 0 at the second, 1 at the second position and 0 everywhere else, and so on. By this method, you obtain a basis for Rn. Okay. So this particular basis is called standard basis. Okay. For Rn. So let's say for R2, this would look something like 1 0 and 0 1. Okay. you can say that, see that, like if you have any element x comma y, you can write it as x into, let's say this is v1 and this is v2, x into v1 plus y into v2. And if you remove any of the element, so let's say if you removed this one, you removed this, then you won't be able to generate any vector which has a non-zero entry at the first position, right? So so you can't remove any element out of it. Okay, so something like this is called as a basis and their associated dimension. Second space that I want to mention is second space is something called as polynomial space. So I'll call it P and R. So this is polynomial up to degree n. Okay, so so you know what, how a polynomial look like, right? X cube plus 2 plus x, let's say. Okay, so PNR is a vector space having polynomials up to degree n. Okay, so you can have polynomials starting from degree 0 up to degree n that in that particular set. Okay, so standard basis for this is, so standard basis for this is 1 x x to the power n. So what is the dimension of P and R? Dimension of P and R is n plus 1. Okay. Okay. One more standard basis is for set of n cross n matrices, n cross m matrices. So you can make first element as 1 at the first position and 0 everywhere. And in the second matrix, you can make 0 in the second place and 0 everywhere, and so on. Okay. So one question that is coming to my mind we can solve is, so let V be a vector space of all n cross n matrices. Okay. Then what is, so let's say, then we define a subspace W. W is a subspace space of V containing all symmetric matrices. Okay. Then what is dimension of W? Okay. See, one approach to find dimension of any particular vector space or a subspace is to look at a basis set, and then you see how many elements are there, and then you can like just count it and say like these many elements are there, so this is my dimension. But sometimes it is not very time saving, or I would say computationally easy to list down all the basis elements. Okay, in those kind of things, those kind of times, one thing that you can remember is, so if you have some subspace W, okay, then the dimension of W is nothing but number of independent choice. Okay, this is the one line that you can remember. So it is the number of independent choice that you have to make in order to construct this element of W. Okay, so for example, right now we had a case of symmetric matrices. So let's say we have a matrix. Okay. Let's take a simpler example, then we will go to case of all symmetric matrices. Okay. So let's say we have a set, let's say W star, which is set with uh, only first row being non-zero. So this is a matrix in which only first row is non-zero and everything else is zero. Okay. So let's look at an element of this particular set. Okay. How would that element look like? So it will have some entries on these positions and rest everything is zero. Okay. So if you want to make an element of this set, okay, so you have this place to fill of your choice. You can choose anything to fill over here if you want to construct a element of this particular set. You can fill anything over here, but wherever you have zero, there you don't have any choice at all, right? There you can't decide what you have to fill. Okay. So if this is an n cross n matrix, how many choices you have to fill? You have to fill n such choices. Uh, Whoever raised hand, you can either type or you can speak straight away. I think that hand raised was by mistake. Or yeah. Okay, so you have n choices to make. That's why dimension of this W star would become n. Okay. And if you want to construct now basis from here, you can simply take 1 over here where you made your first choice and 0 elsewhere. Okay, for the second thing, you can take second position where you made any choice as 1 and 0 elsewhere. Okay, so this is how you can further construct a basis out of it. Okay, now getting back to our previous example where W was a set of symmetric matrices and we have to find dimension of this particular set. Okay, now how do we do? Again, as I said, we just need to see what are the number of choices that we have to make. Okay, so this is our matrix, let's say. Okay, what is the property in a symmetric matrix? Okay, let's see if we have these many positions to fill. Okay, so I can choose anything of my choice over here, whatever I want. That won't make any difference. So let's say I can choose this particular thing. Okay, now let's move to the second position. I can choose anything over here of my choice, right? But if I choose anything over here, what will happen? Like if I have a symmetric matrix, then this entry and this entry must be same. So I make a choice over here. That means I'll block any choice possible for this particular thing. Okay. Again, if I move over here, I'm blocking this particular choice. Okay. So if you look carefully, how many choices we have to make is just for the upper triangular matrix, or you can say the lower triangular matrix, whatever way you are comfortable. If we make choices for these entries, then the rest of the entries get filled on their own. Okay. So what would be the dimension? So in first row we had n choices to make. In second row we had n minus 1 choices to make, and so on till last row. So this is n into n plus 1 by 2. So for set of all symmetric matrices of size n cross n, the dimension is n into n plus 1 divided by 2. Okay. Similarly, you can look at skew symmetric matrices. In those matrices, you have these diagonal entries to be 0. Then the diagonal entries also don't contribute, and then you would have some of like you will have choices over here, here, and then you can write it as similar sum. and that would be, I guess, n into n minus 1 by 2. Okay. So yeah, like if you have been asked to evaluate dimension of some subspace, then you can use this approach to find the dimension. Okay. When I was giving my jam, I guess there was a question based on this symmetric matrix thing, dimension. That's why this question kind of came to my mind, right? Okay. Okay, any doubt related to this till this point, then I'll move ahead. Any related thing you want to ask that you might have came across related to vector spaces, system of linear equations, eigenvalue, sorry, echelon form, or basis, linear independence, dependence. Okay. Okay. So now we have defined something called as vector spaces. Now we want to look at a special kind of function between these vector spaces. Okay. So the kind of function that we are looking at is called as linear transformation. Okay. Transformation is just other name for function. So if you have u and v as your vector space over some field f, okay, then a function from u to v is called a linear transformation if it satisfies these two properties. Okay. Okay. What is the difference between a row echelon form and row reduced echelon? I think I forgot to mention about row echelon, reduced echelon form. Thank you for reminding me. Okay. I'll be very informal. I won't technically define, but I'll try to explain very informally. Okay. So, if you remember in row echelon form, what we had, so below every pivot element, we should have all zeros, right? And so if you have a pivot element over here in this row, then in the next row or any subsequent row, if you have a pivot element, that should be towards the right of this element. Okay. So something like this. Okay. So this is a something called as row echelon form. So for example, this particular example is in row echelon form, right? Now, what is row reduced echelon form? In row reduced echelon form, what you do is you impose an extra rule. So what is that extra rule? Extra rule is any entry above pivot element must be 0. So till now what we were saying is that if you have a pivot element, anything below that should be 0. Now what we are saying is in a row reduced echelon form that anything above the pivot element also should be 0. So we need to make this thing also as 0. Okay. So this in a row reduced echelon form would look something like 1 0 1 0. Okay. So this is the only difference between row echelon form and row reduced echelon form, that in a reduced echelon form, okay, we have an extra property that anything above the pivot element should also be 0. So I'll give you a 3 cross 3 example also, just for you to understand. So this is 1 0 0 2 1 0 0 0. Let's take it as 3 0 0. Okay. So this is your row echelon form. If you see, it satisfies all the property that your pivot elements, anything below the pivot element is 0. Okay. And if you have a pivot element in the lower row, that should be the right, towards the right of the pivot element of the earlier row. That is true over here. But it is not satisfying one property, that anything above the pivot element also must be 0. So if we make it satisfy that property also, so this is 1 0 0, 0, 1, 0, 3, 0, 0. Now this is in row reduced echelon form, that anything above the pivot element should also be 0. Is it clear? You can type in the chat box if it is clear. If it is not, then also please type. Thank you. Okay. We were talking about linear transformations. Okay. So linear transformation is a function between two vector space satisfying these two properties. Okay. So if you have x and y elements of your vector space and you take their sum and you take function of that, that is t of x plus y, that would be same if you took t on x first and then you added it to t of y. This is my first property.
There is
Yeah.
something that in row reduced form, I mean, we put all the zero rows in the bottom of the matrix.
That we do also in row echelon form, right?
Yeah.
Yeah. Yeah. Yes. Okay. Yeah. So next property is that if you have a scalar multiplied with x, then t of cx would, then c would simply push out. Okay. So I think I don't have a example of linear transformation over here, but yeah, I would have it in some week. Yeah. Mm, just a second, sorry. Yeah. So here I have many examples. So this is a simple example of linear transformation. So if you have t of a1 going to a2, this
Can
a1
you
a2, yeah,
can you please increase the font? Visible
sure.
font.
So this is an example of a linear transformation where a1 and a2 goes to 2a1 plus a2 and a1. You can satisfy, like you can easily verify this would satisfy both this property. I'll give you another intuitive example, c times t of x. Okay. I'll give you another intuitive example that is called rotation by angle theta. Okay. So you have some vector v in R2. Okay. So what is my transformation theta? That we are rotating this particular vector counterclockwise by some angle theta. Okay. So what it is saying is, so if you rotate a particular vector x by theta, okay, and you also rotate a vector y by angle theta, and then you take their sum, that should be same as if you take the sum of this vector x and y first, and then you rotate that particular vector x plus y by the angle theta. Okay. So this sort of appears intuitive, right? So, or the another example is, so if you have, let's say a vector v, and you take its projection onto x-axis, okay, and then you had another vector y and then you took their sum and then took their projection, or otherwise you first took their projection and then took their sum. These two things should be same. And the second property is sort of also very easy to see, that your transformation of your cx, that is if you are multiplying it by some scalar, then that scalar should come out. Okay. So if a function is satisfying these two properties for you, then that particular function you will call it as linear transformation. Okay. So now a important theorem from where a lot of questions can arise in case of linear transformation is something called as rank nullity theorem or the dimension theorem. Okay. So what does this theorem say is, so if you have a function t from v to w, Okay. Then dimension of your VE, okay, is equal to nullity of T plus rank of T. Okay, now I'll define what is rank and nullity for you. So you might have came across something called as zero of a polynomial, right? Or so you used to find zeros of a polynomial. What does the zero of a polynomial used to do? If you replace that thing in that polynomial, you'll obtain the answer as 0. Okay. So x belongs to nullity of T if T of x is 0. That is the mapping of your, I won't say nullity, I would say null space of T. Okay. This is null space of T. Okay. So all those elements which are getting mapped to 0 by this function belongs to null space of that T. And if you look at the dimension of this space, so this space that you will get, this will form a vector space in itself. This will form a subspace. Okay. Then if you look at the dimension of this null space, okay, that is called as nullity of your T. Okay. This is one thing. Second thing was rank. Okay. What is rank of T? So you have range of T. You have some range space of T. If you took a transformation T, you obtained some result. So whatever is the range space of T, this is also a subspace of W. Okay. This would now form a subspace of W. Yeah, hello. Okay. So this forms a subspace of W. Now, if you take the dimension of this set, that is your range of T, if you take dimension of range of T, this is something that is called as rank of your transformation T. Okay. So this is another sort of important theorem that is there, that your rank plus nullity is equal to dimension of V. One thing that I didn't include it, but I find is slightly important, is that how do you check if your T is 1, 1 or not? So if you have a linear transformation, okay, you want to check if your linear transformation is 1, 1 or not. Okay. One simple way to do is that if your nullity of T is 0, or the null space of T contains only element 0 in it, then your T is 1, 1. Otherwise, it is not. Okay. So you can very well prove that T is 1, 1 if and only if null space of T is 0. Okay. How do you prove it is, let's say if your null space is not 0, null space of T is not 0, then what does this mean? You have two elements at least, x1 and a 0, okay, and this x1 is not 0, such that these two elements are getting mapped to 0. Okay, what does this mean? This means that T is not 1, 1, because two different elements are getting mapped to the same point 0. Okay, now other way, let's say that your n of T is 0, then you need to prove that T is 1, 1. So whenever you have to prove if and only if, you do two things, that you let this thing and then you prove the other thing. And for the converse part, you assume this thing and you prove the first part. Okay. So for this thing, if you assume that your nullity of T is 0, okay, then you want to prove that T is 1, 1. So let T of x1 be T of x2. This implies T of x1 minus x2 is 0, right? I just took this T on the left hand side and then push this x1 inside using the property of my linear transformation. Okay. Then now I know that my nullity of T is 0. So the only possibility that x1 minus x2 is mapped to 0 is that my x1 minus x2 is 0 itself. Okay, so this means that my x1 is x2, or this thing would imply that t is 1 1. Okay, so this was another important property that I think can be useful. Another thing is that yeah, I haven't included it here, but I'll include. Okay, so one more thing is that for every transformation T, you can find a matrix representation. Okay, so for every transformation T, you can find a corresponding matrix to it, and for every matrix A, you can find a corresponding linear transformation to it. Okay, so for example, I'll solve a very simple example. The example that we saw, I'll try to solve that only. Do we have, yeah, we have here. Linear transformation, yeah. We will try to find a matrix for this particular linear transformation. I'm pasting it here now. I hope font is big enough. Font, yeah. So whenever you need to find a matrix for a linear transformation, you need to make two choices. That is for basis of your set U, let's say this is U to W, then you need to pick one basis for W and one basis for your U. Okay, and easiest thing to pick is your standard basis. Then your calculations becomes pretty easy. Okay, so right now we have both the sets to be same, that is R1 and R2. This is R2 and R2. So I'll take beta 1 and beta 2 to be a standard basis for R2. Okay, so whatever matrix representation you get, that is unique with respect to the choice of beta 1 and beta 2 you make. If you make some other choice of beta 1 and beta 2, you will get a different matrix. Okay, so what is my standard basis for R2? This is 1 0 and 0 1. Okay, now what you need to do is you need to find T of beta 1, that is transformation for every element of beta 1. Somebody's mic is making noise. I'll mute that first. Yeah. Okay. Then what we do is we find the transformation of every elements of beta 1 and then try to represent whatever output we get in terms of elements of basis beta 2. Okay. We'll see how we do it. So let's first of all calculate T of 1 0. Okay. What is T of 1 0? This is 2 times A1. So this is 2 plus A2. This is 0. And the second element is A1. Okay. Now we have obtained it to be 2 1. What I said next is that we want to represent this in form of elements of beta 2. My beta 1 and beta 2 are same. So we can write it as 1 0 plus 1 times 0 1. Okay. So now we need to find this thing for the second element also. What is this? This is 2 times A1 plus A2. So this is 1 0. This is nothing but 1 times 1 0 plus 0 times 0 1. Now how do we write this particular information that we have got in matrix? What we do is then A is, so whatever coefficients you have got from the first element, you write that thing as the first column of your matrix. Okay, so this would be 2 1. Okay, and again for the second column you write whatever you have got from the second element. This is 1 0. Remember that you should maintain the order of this basis thing, then only there would be some like uniformity. So this is the matrix that you can obtain for this particular linear transformation. Okay, and if you want to reach from a to t, then just multiply a by some x, you will get whatever is the output for x. Okay, that is your t of x is nothing but a of x. Okay, so now after this I'll move to something called as eigenvalue and eigenvectors. That was my plan for today, that I'll revise this basic vector space stuff, then some linear transformation, and then eigenvalues. Yeah, Gopinath, if you want to ask something, you can ask straight away. Or anybody else has any doubt, he or she can either unmute himself or herself or can type in the chat box. Anything related to whatever we have discussed till now. Okay. Gopinath, if you want to ask anything, you can either unmute yourself and speak, or you can type it in the chat box. Okay. Okay. So I won't go into details that why do we find eigenvalues and eigenvectors. I'll just try to tell you how do we find eigenvalue and eigenvectors, because we have already covered I think 2 lectures on eigenvalue and eigenvectors. So right now I just want to revise like how do you find out eigenvalues and eigenvectors. Okay. So first thing is that eigenvector or eigenvalue can be found for a linear transformation T. Okay. So there is a very simple definition for eigenvalue or eigenvector. I won't go into this complete definition. So if you have a non-zero vector v satisfying this particular thing, that if you input v into t, then you just get a scalar multiplication of that particular vector only v, then v is called an eigenvector and lambda is called an eigenvalue for that transformation. Okay. So what property should satisfy? That first of all v should be non-zero and t of v should be lambda times v. Okay. Now this is the definition for your eigenvalue and eigenvector. Now if you want to find this lambda and v, how do you proceed? So I'll go step by step. If you take this thing on the left hand side, what you get is a 0. Okay. Now t of v is nothing but let's say we have some matrix representation for t as let's say t, then t of v is nothing but tv minus lambda v is 0. Okay, then t minus lambda I times v is 0. Okay, now as I said that I want my v to be non-zero. Okay, when can I get my this thing to be non-zero? If this particular, this is a system of equation, right? This is a, this is x, this is b. Okay, so if this system of equation has a non-zero solution, okay, then I would get a non-zero v, right? Now if you have a system of equation ax is equal to b where your b is 0, okay, that is Ax is equal to 0, then if you take x is equal to 0, that is always a solution for this kind of system, right? So if you want a non-zero solution, the only option that you have is that Ax is equal to 0 must have infinitely many solutions. Okay. Now, if you recall, in what case did we have infinitely many solutions? That rank of A is strictly less than n is equal to rank of, uh, yeah, this was, and rank of A was equal to rank of A augmented with B. Okay. So we should satisfy this particular property, that rank of your T minus lambda I must be strictly less than n. Or what does this mean? That T minus lambda I must not be invertible. Okay. When is a matrix not invertible? If determinant of T minus lambda I is equal to 0, then this is not invertible. Okay. So just to conclude whatever we discussed right now is that if you want TV to be lambda times V, then lambda must satisfy determinant of T minus lambda I is equal to 0. So whenever you have been asked to find eigenvalue or eigenvector, the first thing that you do is you find eigenvalue that satisfies this equation. Then you use those eigenvalues in this particular equation to find eigenvectors. Okay. So I'll do a pretty simple example. Okay. So I have been asked to find eigenvalue for this particular matrix. What I'll do is I'll also find eigenvectors corresponding to it. Okay. So as I said, step 1 is to find eigenvalues. And what does eigenvalue satisfies? Eigenvalue satisfies determinant of A minus lambda I is 0. Let's put it in this. So this is, if you subtract A minus lambda I, you obtain 2 minus lambda, 2, 5, minus 1 minus lambda. And this determinant should be 0. Okay, let's evaluate this determinant. This is lambda minus 2 into 1 plus lambda, okay, minus 10 is equal to 0. Let's simplify it and solve it. So this is lambda square minus 2 lambda plus lambda minus lambda, and minus 2 minus 10 is equal to 0. This is lambda square minus lambda minus 12 is equal to 0, or this is lambda square minus 4 lambda plus 3 lambda minus 12 equal to 0. This implies lambda minus 4 plus 3 lambda minus 4 is equal to 0. What does this give? This gives lambda is equal to minus 3 or lambda is equal to 4. So whatever values of lambda you have got, those are your eigenvalues. So what are the eigenvalues for this given matrix? Eigenvalues are minus 3 and 4. Okay. Okay. Now let's try to find eigenvector. Okay. So eigenvector for lambda is equal to minus 3. Okay. What does this satisfy? This satisfies that A minus 3i into V must be equal to 0. This came from here, that A into V should be minus 3 times V. I just took it this side to make it 0. Okay. So I need this particular thing to be satisfied. So my A is 2 to 5 minus 1, 2 to 5 minus 1, yeah, plus 3003 into some V1 and V2 must be equal to 0. Okay. So what does this imply? This is 5, 0, 0. This is not 0. This is 5, 2, 5. Again, this is 2. V1, V2 is equal to 0. So what does this implies? 5V1 plus 2V2 is equal to 0. Okay. Now if I took my V1 to be 1, what do I obtain? V2 is minus 5 by 2. So a eigenvector, you remember that eigenvector is never unique. So you just have like, so this forms a vector space, right? You can choose a representative of it and call it eigenvector. So if that space that you are getting is of dimension 1, so you can take one representative out of it. If you are getting the eigenspace of dimension 2, then you should pick two linearly independent representative out of it. Okay. So an eigenvector is 1 comma minus 5 by 2. Okay. And similarly, you can find for lambda is equal to 4, again using this particular condition with 4 over here, what I obtain is I obtain minus 2, 2, 5, minus 5, V1, V2 is 0, or I would obtain minus 2V1 plus V2 is plus 2V2 is equal to 0, or V1 is equal to V2. So an eigenvector for lambda is equal to 4 is 1 comma 1. Okay. So this is how you can find eigenvector course an eigenvalue for a particular matrix that is given to you. Okay. Now on this line we have something called as similar matrices. Okay. In linear algebra, you call two matrices A and B to be similar if A is equal to XA X inverse for some invertible matrix X. Okay. So we are talking about eigenvalues and eigenvectors. Okay. So let's say yeah, you have a matrix A, okay, and you found out this thing, determinant of A minus lambda I. Okay. Whatever, so when you were solving this thing, that determinant of A minus lambda I is equal to 0, you were getting a equation that you were solving. So on left hand side of your equation, you had a polynomial. Okay. So what we obtained over here, so this is a polynomial on the left hand side, right? So this polynomial has a special name and it is called as a characteristic polynomial. Polynomial of your matrix A. Okay. So if this characteristic polynomial is, let's say, of form lambda minus a1 to the power m1 into lambda minus a2 to the power m2. Okay. So this has split into split into factors like this. Okay. First thing is that it has split into factors like this, and you have, yeah. So now you try to find eigenvectors corresponding to each and every lambda. That is your A1, A2, and AN. So let's say when you tried finding out the eigenspace for A1, you were able to find M1 linearly independent eigenvectors. For this, you were able to find M2 Li eigenvectors, and so on. So whatever is the multiplicity of this lambda minus ai, you were able to find those many linearly independent eigenvectors. In that situation, you call your matrix A to be diagonalizable. Okay. Or in other words, I would give you a simpler definition. What it is meant by a diagonalizable matrix is, if you have a basis in which all your vectors are eigenvectors, then you call your matrix A as diagonalizable. Okay. And this is the equivalent definition, that whatever is the multiplicity of your eigenvalue in characteristic polynomial, if you are able to obtain those many number of linearly independent eigenvectors for every of these eigenvalues, then you call your matrix to be diagonalizable. Okay. This is just the definition. And what is the property of a diagonalizable matrix that I am coming to is, every diagonalizable matrix is similar to a diagonal matrix. Okay. Now I wrote the definition of a diagonal this similar matrix. So what would happen is that my A would be equal to P some diagonal matrix. This D is a diagonal matrix. So how does a diagonal matrix look? You have only element on the diagonals and zero everywhere else. Okay. Into some P inverse. Okay. This is a property of a diagonalizable matrix. Okay. Now, one thing that I want to mention is this: what are these elements of this D and what is this P? Okay. So you can construct D by taking eigenvalues on the diagonal entries. So whatever eigenvalues you obtained, you place it on the diagonal entries and zero elsewhere, then you'll obtain this particular D. So if somebody is asking you like to factorize it in this form, P dP inverse, and A is given to you, so you will find the eigenvalues and the eigenvectors, and you will construct D by placing eigenvalues on the diagonals. What is P? So first column of P is the eigenvector corresponding to the first element that you have placed over here. Okay, you will write it in column form. Again, the second is the eigenvector corresponding to lambda 2. Okay, and so on. If you write it in this form, then you will obtain your matrix P. So let's take example of whatever we did in the previous question. My matrix was 2, 2, 5, minus 1. My matrix is 2, 2, 5, minus 1. I want to write it as some P times D times P inverse. Okay. Now what is my diagonal matrix D? It consists of eigenvalues. So what are the eigenvalues that I obtained? Eigenvalues were minus 3 and 4. So I'll just place minus 3 and 4 over here and 0 at other places. And what are my P's that I'll obtain? So the first column is eigenvector corresponding to minus 3. What is my eigenvector corresponding to minus 3? This is 1 comma minus 5 by 2. What is the second one that we obtained? This is 1 comma 1. Okay. So again, you can find the inverse, and you can write this matrix in this form. If you will do the multiplication, you will definitely get this particular matrix. Okay. So with this, I am hoping to and this eigenvalue thing. If anybody has any doubt related to eigenvalues and eigenvector, please feel free to ask. I just gave you a broad outline uh, for someone who might have missed this lecture or still don't have any idea how to find eigenvalue and eigenvector. So if anybody has any doubt, please feel free to ask. I'll wait for 1 minute if anybody is typing something, and then I'll proceed. Okay. With this, we come to probably the last topic that I'm going to cover today. It is something called as the inner product of a like between two vectors, not of a but between two vectors. Okay. So what is inner product? Inner product is a generalization for angles. Okay. So I won't say angles, but it is a generalization of dot product that we do in Rn. So if you remember that uh, dot product between two vectors is AB cos theta, and using this you can obtain the value of cos theta. Okay. So in similar way, your inner product is used to infer something about the angle between two vectors. Okay. And mainly uh, if you had two vectors which were perpendicular to each other, then what you said is that the dot product between these two vectors must be 0. Okay. Similar to that, if you have this inner product between two vector to be 0, then you call that those two vectors are perpendicular, or in generalized form we call them as orthogonal. Okay. Okay. So what is inner product? Inner product is a function. Okay. This is how it is denoted by two brackets. It is a function that takes as input two vectors and returns a scalar value. Okay. And this should satisfy these four properties. Okay. What are those four properties? That if you have x plus y in the first position, okay, then this thing should split into two parts. That is x plus y dot product with z is x with z plus y with z. If you just look at it with respect to dot product, this is true, right? So the same thing is generalized using this first definition. Now if you have a scalar c x and you take its dot product with y, then you take c out of your inner product. Okay. Okay. Now this property is something that makes it unique. So if you have dot product between x and y and you want to look at dot product between y and x, then it is just the complex conjugate of each other. So what is this symbol? This is complex conjugate. What is complex conjugate? So if you have a plus iota b and you take its complex conjugate, it is a minus iota b. Okay, you might have done this in school. So if you just reverse the role, what you will get is the complex conjugate of each other. And the last thing is that if you take dot product of any vector with itself, then it must be strictly greater than 0 till the time it is not equal to 0. So if your x is 0, then what is this x comma x? That would be 0 if x is 0. Okay. So these are the four properties that uh, you have. Now, the main thing why we defined this inner product is to understand like these vectors from the perspective of angles. Okay. So if x and y is 0, then we call x and y to be orthogonal. Okay. Another thing just to mention that using this inner product, you can define a quantity called as norm. So norm is nothing but length of a vector. Okay. So norm of x is defined as inner product of x with itself. So this gives you length of x. Okay. Okay. So if you have a vector x such that its length is 1, then this kind of vector is called as unit vector. Okay. Now, let's say you have two vectors x and y which are orthogonal. Okay. And both x and y are unit vectors. That is, angle between x and y is 90, or you can say orthogonal, and your x and y norm are both 1. That is, x dot product with x and y dot product with y is 1. Then x and y are called orthonormal. Okay. Okay. Any doubt in this? Then I'll probably move to Gram-Schmidt's process. Okay. Probably this is the last thing that we are going to do today. This is called as Gram-Schmidt's process. So why is this process useful? What this process does is, so if you have, let's say, a basis, not even a basis, if you, let's say you have, if you have a basis, then it's well and good, or if you have a set of linearly independent vectors, then if you do Gram-Schmidt's process, you obtain a set of orthogonal vectors. Now, one thing you should always remember, that orthogonal vectors are always linearly independent. Okay. So what this Gram-Schmidt's process does is that it will convert set of linearly independent vectors into orthogonal vectors. Okay. So what is the process of doing that is, let's say you have v1, v2, vn, which are your linearly independent vectors, and you want to convert them to w1, w2, wn, which are your orthogonal vectors. Okay. Then what you can do is, you take w1 to be your v1. This is the first thing that you need to do. Okay. How do you obtain w2 is, now your w2 is nothing but v2 minus v2 dot product with w1 norm into w1. So basically, what is this quantity representing? Okay, this quantity over here is representing the projection of v2 onto w1. So whatever component v2 has that is inclined with w1, we subtract that particular component from v2, and whatever is left, whatever we get, is orthogonal. So now w1 is orthogonal to w2. Okay. Similarly, if you want to obtain w3, what you will do is v3 minus v3 dot product with w1 to w1 minus v3 dot product with w2 and 2 to w2, and so on. So if you have more and more vectors, you can proceed in this way. Okay. I think I have an example from last week. I'll just go through that example. Okay. Yes. So here we have what I said, that okay, there they have changed the notation. Okay, so as I mentioned, so here we have mm, three linearly independent vectors, W1, W2, and W3. We want to convert them to orthogonal vectors using Gram-Schmidt's process. Okay. As I mentioned, first vector we should choose as it is. Okay. So we took V1. So remember that I was converting V1, V2, Vn to W1, W2, Wn. Here there is a slight flip in notation, that we want to convert W1, W2, Wn to V1, V2, Vn. Okay, this is a slight change in notation. So we take V1 to be W1. Okay. Now for the next element, we take V2 to be W2 minus W2 dot product with V1, V1 norm by V1. So if you look at the calculation carefully, so this is W2, we have written 1, 1, 1, 1 over here, minus W2 norm with V1. So we have V1 to be this. If you take its dot product with this becomes 1 into 1 as 1, plus 0, plus 1 into 0. So this becomes 2. Okay. And if you take just the norm of V1, that is V1 inner product with V1, this is 1 into 1 plus 0 plus 1 into 1, again 2, that is 0. So this would again we would obtain as 2. Okay. Okay. So this is what we obtain, and then we obtain V2. Okay. Similarly, calculation is done for V3. Okay. One thing I think I messed up over here is that this norm is square root of this inner product, not just the uh, inner product with itself. This is square root of this. So norm of x square is dot product of x with x. Okay. Any doubt in this thing or anything else in this course? I have 10 minutes left. I'll be happy to address. So I'm not sure when your exam is, the exact date, but I can recommend 2 or 3 books that you can definitely read and practice that would be beneficial for. First book is Linear Algebra by Friedberg. This is my sort of favorite book. It has both theoretical as well as computational examples. You have numerical as well as some theoretical proof kind of examples, and that is by far related to the level of the course that was taught. So not all chapters will be relevant, and so you need to pick whatever is relevant for you. Okay. Another book is your Linear Algebra by David C. Lay. Okay. This book is sort of more simpler written, and the questions are more focused on numerical questions, and you will find lot of numerical computations being carried out in examples. The book is also more colorful as compared to the previous one. So if you are doing your first linear algebra course and haven't read any book till now, so this can be a good book to start with. So all these books you can easily download from LibGen. Okay, so you can download and read. These 2 books I think would be more than enough for the level of course that was taught. Now, if anybody else has any question, please feel free to type it in the chat box or unmute yourself. I'll end the recording and I'll wait for your question.